Today we will go over the test method ASTM D7823, which provides a procedure to identify and also quantify phthalates by thermal desorption gas chromatography mass spectrometry. 6 phthalates are used to demonstrate the use of this procedure, and the phthalates are BBP, DBP, DEHP, DNOP, DINP, and DIDP. And here you can see the actual official title of the method from the ASTM website that is also available for you to purchase. So as we all know, phthalates, which are phthalic acid esters, have been used to manufacture a wide range of consumer products. They can be added to plastics to make them more flexible and harder to break. And although the widespread use of phthalates in polymeric products has been largely discontinued, but they still pose a risk to human health. Phthalates are actually easily released into the environment because they're not covalently bonded to the polymer. So as a result, exposure can be through direct contact with food, water, and the atmosphere. Several phthalates are regulated on a global scale. United States, Canada, European Union, Japan, and many other nations have actually banned the use of and passed regulation designed to monitor the concentration of phthalates in consumer products. And here you can see some of the regulations with the references, substances, and requirements as example. So it is very critical for different manufacturers to comply with these regulations by having the capability of accurate measurements of these phthalates. One of the traditional techniques for analyzing phthalates is solvent-based techniques to extract the phthalates from the polymeric mixture. The extract is then analyzed using GC or HPLC to separate and quantitate the individual phthalates. These traditional techniques are most of the time time-consuming, costly, and they do not always completely isolate the phthalates from the polymeric mixture. As a result, reproducibility and accuracy can become challenging. On the other hand, thermal desorption uses sufficient amount of heat to thermally vaporize a sample without oxygen and thermally extract or isolate the additives, in our case the phthalates, from the polymers and heavier portions of the sample. So as we just mentioned, the traditional techniques require large amount of solvent, excessive analysis time, and can be prone to contamination and the other errors. The result of this additional sample handling can reduce laboratory productivity, and the information obtained could exhibit poor precision and accuracy in most cases. So that's really where thermal desorption GCMS comes in place as a green alternative to solvent-based extraction techniques. Thermal desorption GCMS is actually ideal for any type of solid samples. It requires very small to no amount of solvent. It adds efficiency to your laboratory and also improves data quality. This technique is used in other applications and industries, as you can see here. For example, brominated flame retardant and rubber manufacturers also can use this technique. But today we will mainly focus on phthalates in polymers, especially in a PVC type sample. So before we go over the application, we're just going to talk a little bit about thermal desorption GCMS. And here is the system configuration for a microfurnace pyrolyzer, which can perform pyrolysis and thermal desorption type analysis. The microfurnace pyrolyzer, which is shown as number 2 in this figure, is used as a programmable temperature inlet to your GCMS system. It is directly connected to your GC injection port, so there won't be any transfer line, there is no active site, and there is no cross-contamination. You can also see some of the other accessories in this figure. For example, the microjet cryo trap that uses liquid nitrogen to trap and focus lights and volatiles at the head of the GC column for you. The selective sampler that is used for the hard cutting mode of operation. The AutoShot sampler for automating the analysis of up to 48 samples. the vent-free GCMS adapter that allows switching the columns without venting DMS, and the F-Search interpretation libraries to identify polymers and additives. So what sets a microfurnace technology apart from the other pyrolyzers in the market? With a microfurnace, sample introduction is nearly instantaneous. The sample is actually placed in an inert sample cup and is held near ambient temperature in helium. The microfurnace is then preheated to the desired temperature, which is precisely measured with a thermocouple sensor. The sample cup then dropped into the quartz pyrolysis tube where the sample is pyrolyzed. The pyrolysates are then swept directly onto the GC column for separation and detection by MS. This technology is based on a continuous mode pyrolysis, where all the pyrolysate as they are generated directly and continuously transfer to the GC column. The sample is held at an ambient temperature while the furnace is preheated, so the sample is not going to be exposed to any heat prior to the analysis. And as a result, there won't be any degradation or any evaporation of the lighter compounds before the analysis starts. Also, with microfurnace technology, you can perform thermal and multiple separation analysis. For example, you can perform evolved gas analysis, thermal desorption, flash pyrolysis, double shot, and hard cutting. But today, we will focus on the evolved gas analysis and thermal desorption modes of operation in microfurnace. Now, to chemically characterize an unknown sample, we have developed a series of techniques that is called the method map. The method map provides two simple steps for determining the organic composition of any type of unknown sample, liquid, solid, or even gas type sample. Evolved gas analysis, which is known as EGA, is your first step, which provides a clear picture about the thermal profile of your sample. EGA is a thermal analysis very similar to TGA, a thermal gravimetric type analysis. But with EGA-MS, you can identify the chemical composition of the evolved gases at different temperature. The second step is then to use your EGA thermogram to define the thermal zones of interest and then perform separation analysis on your sample. So EGA really guides you on what to do next. It will show if a thermal desorption, hard cutting, or flash pyrolysis is needed, or if a combination of these techniques is required. Now that we have a good understanding of microfurnace pyrolyzer and its capability, let's go over the actual phthalate application. So the ASTM D7823 sample preparation specifically calls for the dissolution of the polymer in a suitable solvent such as THF. However, subsequent studies have also shown that meaningful data can also be obtained with, when the polymer is analyzed directly. So here, as shown here, there are two techniques for sample preparation, direct and thin film. Analysis of the solid is often referred to as a direct analysis, in which you can simply crush and powder your sample, and then you can place a few micrograms directly inside your cup. On the other hand, you can also use a thin film method, in which you dissolve the powdered sample into solvent and then analyze a microliter aliquot of a quantitative solution of the sample. The RST percentage of DEHP in 4 runs of thin film and direct approach was calculated to compare the influence of the sample preparation method on the precision. The thin film method is an aliquot of a solution, as we mentioned, that is by definition homogeneous, whereas the direct method is a random sampling of particles which could lack sample-to-sample reproducibility depending on the sample type. The RST percentage of DEHP for the thin film is about 1.1%, whereas the direct method generates a 4.7% RST. So to show the importance of sample homogeneity in measurement accuracy, DHP was also quantified in each part of this plastic toy shown here. You can see that different ppm amounts were detected in each color part of the toy. So again, it is very important always to consider sample homogeneity when you're performing quantification analysis. And sample homogeneity can be accomplished using various methods, including cryomilling, grinding, averaging the results from the analysis of multiple samples, and in this example, dissolving the entire sample in a known volume of solvent. But regardless of how the sample is homogenized, only microgram quantities are analyzed using the thermal desorption GCMS. As we just learned from the method map concept, evolved gas analysis, known as EGA, defines the optimal thermal desorption zone for thermally extracting the phthalates. EGA is a rapid screening method that utilizes the temperature programmability of the microfurnace pyrolyzer. Now, to perform EGA, a deactivated stainless steel tube connects the injection port to the MS. The sample is heated, typically from a low temperature to a higher temperature, and as the temperature increases, gases evolve continuously from the sample, pass through the tube, and are detected by the MS. A plot of sample temperature versus detector signal is then called an EGA thermogram. Now, to further analyze the sample, the EGA tube is switched to the GC separation column using the vent-free GCMS adapter. The microfurnace is then programmed to the desired or optimal thermal desorption temperature range, and a separation analysis is performed on the sample to thermally extract additives and lighter compounds from the heavier and polymeric portion of the sample. The EGA thermogram of a PVC sample heated from 100 to 700 C with a ramping rate of 20 degrees per minute is shown in this figure. Extracted ion chromatogram, or EIC, are also used to identify the thermal zone over which the phthalates evolved from the EGA thermogram. As we all know, ion 149, which is a common to all of the phthalates of interest, was used here to identify the phthalates envelope. Now, in this example, DOA, which is a common plasticizer used in manufacturing of flexible plastic toys, or medical devices, or food packaging, it actually desorbs along with the phthalates. So to identify and quantify the phthalates in the sample, it is necessary to either chromatographically separate the DOA isomers from the phthalates of interest, or you can use ions that are present in the phthalate mass spectra and not found in the DOA spectra. Also here, I want to mention one of the most important advantages of the thermal desorption over the traditional solvent-based technique is that with thermal desorption, only the portion of the desorbed sample is transported to the column. Now, if you look closely here at the thermal desorption zone for the phthalates, you'll notice that only the phthalates thermally evolved from the sample at about 320 degrees Celsius. And this means that the polymer remains in the sample cup and is not introduced into the GC inlet column, or MS. And because the bulk of the sample, which in this case the polymer fraction, remains in the cup, more sample amount can also be placed in the sample cup to improve the signal to noise of the target compounds. So this is the desorbed portion of the PVC sample shown on a previous slide. The identification of each compound is based on the retention time, the presence or absence of the quant ion, and one other confirming ion, as you can see here. And as we all know, polymers are loaded with additives. DINCH is commonly used, and it actually co-loads with several of these phthalates. So it is necessary to find unique ions to use for the quantification. Also, using a standard addition to calibrate helps to take matrix interferences into the account. A section in ASTM D7823 shows the analytical precision of thermal desorption GCMS when analyzing the regulated phthalates, and you can see that table here. This is a summary of run-to-run precision for 3 different PVC samples. Each PVC sample contains 1 additional plasticizer that actually co-desorbs with the phthalate. Phthalate concentration is 1000 ppm, and this data shows how a unique quant ion can be used to calculate the phthalate concentrations with high accuracy and low RSD percentage. This figure summarizes the data quality differences in accuracy and precision between the thermal desorption and solvent extraction techniques. So wet chemical methods or those solvent extraction techniques often result in low values for the concentration of the volatile phthalates. These can be attributed to losses during sample preparation. And as shown in the ASTM figure here, you can see when solvent extraction was used, phthalates such as DBP, BBP, and DHP, they had pretty high value. And actually, you can see that they are with high RSD and lower value than the theoretical value of 0.1%. Also, with solvent extraction approach, high concentration values for DNOP, DINP, and DIDP are resulted, which is due to the interference from the co-loading with DINCH. On the other hand, the thermal desorption technique that is shown here as a blue curve gives an almost constant response for all the 6 phthalates, very close to a theoretical value with an average precision of 1.8% RSD. And this accuracy can be obtained as the phthalates are thermally extracted from the mixture and unique quantification ions are used to distinguish them from one another. As we learned, individual phthalates are identified using both retention and mass spectral data. However, attention must be given to the possibility that they are similar compounds which co-load and have similar mass spectra to the phthalate of interest. One such compound is DOTP, which is very similar to DNOP. With thermal desorption GCMS, you can actually easily and accurately identify DNOP and DOTP, even though both compounds co-load with various DINCH isomers by using M/Z of 279, which is free of interference. In addition, DOTP has a 261 ion, DNOP and DINCH do not, which provides a confirming ion for DOTP. ASTM D7823 is written specifically for phthalates in PVC. However, the solubility of phthalates in most non-crystalline polymers could be the same. As a result, the thermal desorption temperature range is independent of the polymer substrate. When using thermal desorption to isolate beyond the scope of this ASTM D7823, or if they are incorporated into a polymeric base that has not been evaluated, it is recommended to verify the optimal thermal desorption zone using your EGA-MS first. In addition to the ASTM D7823, we also have IEC 62321, which is for identifying phthalates in power cord, so that's for electronic type devices. The IEC method uses the same concept as the ASTM by using EGA as the first step for identifying the optimal thermal zone to thermally extract the compounds of interest. Once the EGA thermogram is obtained, the additives, in this case the phthalates, were thermally isolated using separation mode of operation from the microfurnace. Well, at the end, in summary, ASTM D7823 is based on a thermal desorption GCMS technique. The method is suitable for an extended list of phthalates in a wide range of polymeric compounds. The entire analytical sequence is performed in a single step in which a known weight of a solid sample or a known volume of a quantitative solution is placed in a sample cup, which in turn is placed into the autosampler carousel. Thermal desorption also eliminates conventional sample preparation. The sample is heated, so the foul is thermally dissolved from the polymer. It is fast, it uses a minimal volume of solvent, eliminates the need for expensive glassware, and more importantly, delivers accurate and more reproducible measurements.